So a quick review of drawing Lewis dot diagrams. For single elements, what we would need to find is the number of valence electrons. We can either determine that by writing out the configuration and looking for the valence shell, totaling up those electrons, or if you remember from Gen Chem, we can use a shortcut where we look at the group number that is at the top of the column that the element happens to be in, and the ones digit of that group number is the same as the valence electrons that you have. Now this only works for the S and the P block, the main group elements, but it can be a handy shortcut to getting that value. And so then what we would do is just distribute one electron, kind of like you're dealing cards in a card game, one to each side of the element symbol, and then you would double up once each side has one electron. And this roughly mimics what we saw with Hund's rule. So if we look at these elements, carbon has a total of 6 electrons, configuration 1s2, 2s2, 2p2. So in the second shell, which would be its valence shell, there's a total of 4 valence electrons. If we look on the periodic table, carbon is in group 14, so that ones digit, as I said with the shortcut, gives us the total number of valence electrons that we would have. So distributing those electrons around the C for carbon, we'd have one on the top, one on the right, one on the bottom, one on the left. Why this is important is because for every lone electron that you have, remember every orbital can hold 2 valence electrons. And so if an orbital, which is the space represented on each side of the symbol, for the valence shell, S and P sublevels, if there's only one electron, that means there's space that another atom could come in, share one of its electrons to complete that orbital, and thus create a covalent bond. Oxygen, if we look at its configuration, has a total of 8 electrons, 1s2, 2s2, 2p4. So there's a total of 6 valence electrons. Oxygen's in group 16. And so if we distribute those, if we start at the top, all right, and we go 1, 2, 3, 4, still have 2 remaining, so then we put a second electron in the top orbital, the top space, and then another one to the one off to the right. Ultimately, it really doesn't matter which side you have the pairs on and which side have the single electrons, because again, on paper, a Lewis diagram is basically just a rough schematic. We're not necessarily taking into account the actual VSEPR theory and the molecular geometry and the bond angles that would truly be there. But another important thing to note is that oxygen has 2 half-filled orbitals, so that means that oxygen will typically prefer to form 2 bonds and have 2 lone pairs, whereas carbon would have 4 bonds that it would typically form. Is it possible that they can form other numbers of bonds? Yes, and we'll get into a little bit of that when we talk about formal charges and determining what is the most likely structure to be formed. Looking at the rest of these, fluorine has 7 valence electrons, so that means that all sides except one will be completely filled. Hydrogen has 1 valence electron, so just a single dot. Typically, a single dot would go on the right side rather than the top, but again, it really doesn't matter. Bromine, sulfur, chlorine, and iodine have these structures. And so if we take a look at those, we might notice that there are, some that are very similar to each other. For instance, oxygen and sulfur are right next to each other, and they literally have the same Lewis structure, just a difference in the symbol that's in the middle. And so if we think about why that is, they both end with an S2P4 configuration. Oxygen is 2s2, 2p4, sulfur is 3s2, 3p4. So that similarity in valence configuration leads to similar Lewis diagrams. And as we said, each of those lone electrons is a space capable of a bond. So just like oxygen typically will form 2 bonds, sulfur will also typically make 2 bonds. If we look at fluorine, bromine, chlorine, and iodine, we see that they all have 7 valence electrons. And so as expected, their Lewis diagrams will look very much the same, having only 1 lone electron, meaning that the halogens, which all of these elements are a member of that family, will typically form 1 bond. And so again, we see that elements in the same column typically share similar properties. If we take a look at nitrogen, and try writing the Lewis structure for that, we see that it has 5 valence electrons, 1s2, 2s2, 2p3. And so when we draw that structure, we get 1 lone pair and then 3 half-filled orbitals. Now looking at the periodic table, we see that phosphorus is right below nitrogen, and so its configuration would end in 3s2, 3p3. So we would fully expect and predict that its Lewis structure is going to look very similar to nitrogen's. And so when we consider why nitrogen tends to form compounds with the same elements in the same sorts of ways that phosphorus does, the reason that it has those similar bonding properties is because of their valence electron configurations and how similar they are. Even though they're in different main energy levels, the distribution of them is the same. So when we start looking at drawing Lewis diagrams for entire organic molecules, it's going to follow much the same process that it did when we looked at drawing Lewis electron dot diagrams in Gen Chem. The main difference is that instead of simple molecules that have just a single central atom, a lot of times organic molecules are going to have more of a backbone, and that backbone is typically made up of carbon atoms. Those carbon atoms can be either linked in a chain, or it can be in a chain, but the two end carbons wrap around and form a ring structure. Sometimes the carbons will form branches off of the main chain, but the bottom line is that carbon forms the backbone of our organic molecules. Once we have that laid out and any other atoms, typically hydrogens or maybe other heteroatoms like oxygen, nitrogen, maybe even sulfur, phosphorus, generally laid out, then we tally the valence electrons. And again, we do that in the same sort of way. Remember that we can determine the valence electrons of an atom based on its electron configuration, or we can look to the top of the element family on the periodic table that the element resides in, and that will give us a shortcut to the number of valence electrons. Again, the ones digit of that group number gives us that number of valence electrons. The first place that we distribute electrons is to connect our atoms together with a bond, so that uses up 2 electrons per bond, and then we make sure that the outside atoms are satisfied for their valence needs. Now the nice thing is a lot of the atoms are going to be hydrogens, which only need 2 electrons to be valence shell satisfied, and the bonding electrons typically take care of that. So it would just be other heteroatoms that might need additional lone pairs to satisfy them. Any extras would go in the central atoms, which again typically is going to be your carbons, but it may be other elements like oxygen or nitrogen depending on which particular structural arrangement you have. The very last thing is most important though, is to make sure that the elements carbon, oxygen, and nitrogen have exactly 8 electrons in them. In the structure that you have drawn. If not, that you're going to need to reassign a lone pair of electrons from somewhere in the structure to create a double bond, or create a second bond, or even a third bond if necessary. So if we look at these structures that we have here, the first one we have is C2H6. So the first thing we would do is put the central atoms, okay, so our carbons form our backbone. And then we've got 6 hydrogens, and each carbon, we already have 1 on each side, so kind of makes sense to put a hydrogen on each of the remaining sides of each of these carbon atoms. So we'll do that. And then to tally up our valence electrons, each carbon has 4, but there are 2 of them, so we're going to double that. Plus, each hydrogen has 1 valence electron, but there are 6 of them. So we'll multiply that by 6, and that gives us a grand total of 14 electrons to distribute. So the first place we're going to put them is to make a bond, so we'll connect the carbons, and then connect each carbon to the 3 hydrogens that surrounds it. Each one of those uses 2, so that's 8 electrons distributed, 10, 12, 14. And so we have distributed all of our electrons, and in checking to make sure that everything's valence satisfied, the hydrogens are good with the 2 from their bond, and then each carbon has 8 around it, which is exactly what it must have. So what we get is the Lewis structure for the simple hydrocarbon ethane. If we look at C2H4, follow the same process. So we'll set the 2 carbons. Now we only have 4 hydrogens. So again, let's start by saying, okay, let's just put 2 hydrogens on each carbon. So we'll do something like that. And so here we would get 2 times 4 is 8 plus another 4 electrons, because we have 4 hydrogens, means that we've got a grand total of 12 electrons to distribute. So we'll go to the bond first. Okay, so there's 2, 4, 6, 8, 10. All our atoms are linked together, but we still have 2 electrons. So what we'll do is, we'll put that on, excuse me here. Okay, we'll have a lone pair on one of the carbons. Now, this carbon is okay because it's got 2, 4, 6, 8, but the right-hand carbon only has 6. So what we have to do is we have to take that lone pair off, and we need to put it in the middle to make a shared pair. So we get a double bond, and hence what we get is the molecule ethene. If we follow the same line of thinking for C2H2, now we only have 10 valence electrons, and so what ends up happening is, to make sure that both carbons are satisfied, we end up having to make a triple bond between the 2 carbon atoms. With C3H8, we're going to link the 3 carbons together, and so when we do that, again, we end up with having enough hydrogens to fill around the carbons, and with the electrons that we have, we are able to form single bonds there. C3H6 is a little different, because here what we have is, if we link our 3 carbons together, okay, so 3 times 4, that's going to be 12 valence electrons there, plus 6 from the 6 hydrogens. So we've got 18. And again, when we start with 6 hydrogens with 3 atoms, kind of makes it seem like, okay, maybe let's start with 2 here, okay, on each one. And when we do that, okay, the first thing we're going to do is distribute to make our bond. So there's 2, 4, 6, 8, 10, 12, 14, 16. We still have a lone pair, one pair, so we might put it, say, out here. Okay, this left-hand carbon is good, the center carbon is good, but the right-hand one is not. So we have to get a little creative with the distribution. We might have to move some things around, and what ends up happening is we actually have 2 options. We can move that lone pair in to create a double bond, which is what we're typically used to, and in doing so, we would have to move one of the hydrogens off of the center carbon, because we don't want to overload that one, giving it 10 electrons. So we could get the first structure that you see there, or what we see is that the end carbon, okay, where that lone pair is, can actually come around and form a bond to the other end carbon, creating a ring structure. And in doing so, each carbon now has its 8 valence electrons. The last example that we see here is methanol and the introduction of the oxygen atom. So that's going to change our valence electrons, 4 from the carbon, plus 3 from these hydrogens, plus 6 from the oxygen, and 1 more for this tail end hydrogen, which gives us a grand total of 14. And the only way it really makes sense to connect these is to have the carbon and the oxygen directly next to one another. Again, when we look at a condensed formula like this, conventionally written this way tells us that these 3 hydrogens are attached all to this first carbon. Okay, so you can't have a hydrogen in a chain, because a hydrogen can't have a bond on the other side. It can only ever form 1 bond. And so when we distribute those electrons, we see that we have 4 left over. The carbon already has its 8, so we can't put them there. They would end up going on the oxygen, and that's good, because oxygen is another one of those elements that must have exactly 8 electrons.